Back to this next session. This is AI, machine learning, and our first speaker is going to be, as it says on the screen, Yishi Ma. Are you here? Or online? It's you! Yeah, hiding from the hide. Okay, you're going to talk to us about machine learning cosmology.
Okay. Hello everyone. My name is Yishi Ma. I'm currently a professor and head of astrophysics at Stanford University Department of Physics. So I've been thinking of coming to this conference for a long time and deliver a message of thank you to CAPC. I think it's a great national facility to help us to do science in South Africa. Today I want to share my passion in machine learning cosmology and show you what CAPC can do in the era of astronomy big data. So just to introduce myself, I started my bachelor degree of physics in Nanjing University and got a master's degree in chemistry in Beijing. Then I went to Cambridge, UK to do a PhD in astronomy. Then I became a Senior National Fellow in Canada, Vancouver, British Columbia. Then I went back to Manchester, UK to do another postdoc, and then I came to UK as a consumer until 2015. Then I stayed for 8 years. Then now I become a Stanford University. So this is basically my career path. So I want to show you my career path synchronized with radio astronomy development. In 2003, when I started my undergraduate, WMAP released the first year data. Then during my master's degree, WMAP released 5-year data. Then we entered into the precision cosmology era. Then since during my PhD period, the Planck of the European Space Agency was launched. So I started to analyze the Planck data and get one year data release when I was doing a postdoc. So I worked on the Planck data by then. Then I came to South Africa, and it was a final release of the Planck data, and we started to work on the South African radio telescope, such as Meerkat, Square Kilometer Array, and Hera. So the reason I come to South Africa is follow the development of astronomical facilities. It's actually a completely working purpose. So this is our understanding of the universe. It starts 13.8 billion years ago as a hot Big Bang. Then the hot plasma mixed the photons, electrons, protons, and neutrinos together. Then around 400,000 years, after Big Bang, the photons decoupled and become relics in the universe because the universe keeps on expanding. Then these photons will just penetrate through the hot plasma and can be observed today. Then after dark ages, the first galaxy and stars formed and they reionized neutral hydrogen. And eventually the modern galaxy formed, like our Andromeda and our own Milky Way. So the overarching question in cosmology are, well, what is the Big Bang? How does the universe evolve? And how does the structure grow? So revolving around this question, the only observation window we have are the cosmic magnetic background radiation, which I just mentioned, the 21 centimeter intensity mapping, and also the galaxies in the low redshift in the nearby universe. So the CMB, the cosmic magnetic background radiation, is a photon relics after Big Bang, which is the earliest observational evidence we can see all the way to the beginning of the universe. And the galaxies certainly we can observe, which is from the 100 years ago, people started to develop the modern telescope, observing more and more galaxies. And this intermediate regime is by the 21 centimeter intensity mapping, which is especially what our own telescope, the SKA and Meerkat and Hera, etc., can measure. So that can use this technique can be used to map out the neutral hydrogen in the universe and therefore probing the epoch of reionization, the first stars and galaxies. So by using the CAPC in the last several years, I did a few projects of machine learning in cosmology revolving around the hot Big Bang scenario. The important projects I did are reconstructing the primordial non-Gaussianity and recovering the cosmological parameters, and finally reconstructing the reionization history of the universe. So this is a famous map of the cosmic magnetic background radiation. So you do see photons that have slightly different temperature distribution across the entire sky. And this is, as I said, a snapshot when the universe was only 400,000 years after Big Bang. Now it's 13.8 billion years. This snapshot was 400,000 years after Big Bang. So really, really early on. And some places the photons are slightly hotter than the other, and the fluctuation is only at 10 to the minus 5 level. But they really encode the primordial fluctuations that imprinted from the Big Bang. So this is really the earliest snapshot we can get. And earlier than this, the whole universe was in the thermal equilibrium, so no light can penetrate through, and therefore we can't probe. The reason we can use this map to probe cosmology is because of the imprint of the quantum fluctuation on large scale on the CMB. And this is a co-moving distance as a function of scale factor. So A equals 1 means today, and the smaller the value of A is, the earlier time is. So this A is essentially a time indication. So during the inflation period, the inflation means the universe scale is exponentially expanding. The quantum fluctuations basically stretch out the Hubble radius, and then they lose causal contact. So this part of fluctuation become independent of the other part of fluctuations. So they become classical fluctuations instead of quantum fluctuations. As the universe re-enters into the radiation domain era and matter domain era, this fluctuation will re-enter into the Hubble radius, and this part of they store the potential fluctuations. Therefore, the gravitational potential in the universe somewhere will be deeper than the others. They will attract baryons and dark matter fall into the potential, and they will collapse and forming structures like the galaxy. So the first project I did is to use machine learning to see if the quantum fluctuation is Gaussian or not. The way we did is to simulate the Gaussian and non-Gaussian component of the CMB map, and then adding realistic experimental effects such as a beam and noise. And then we train the machines from CHPC to form the convolutional neural network. Then we test this with the training data, and eventually we evaluate the precision of primordial non-Gaussianity reconstructions. So this is a simulation we did. For the pure Gaussian map, this is the pure Gaussian map, this FNL parameter indicating the level of non-Gaussianity. So for the pure Gaussian map, if you look at it, one part of the sky is really similar to the others. There's no distinctive feature of this. As we increase value of FNL, you see the map become more and more non-Gaussian. For instance, in this very extreme case, you see some part is obviously redder than the others, and some part is obviously bluer than the others. So previous study in Planck of the European Space Agency used a 3-point correlation function to constrain this primordial non-Gaussianity. But here we want to use machine by directly inputting image into the machine, see if the machine can recognize this non-Gaussian pattern. And here I just fast forward to the result. And you can see that it does. The x-axis is your input value of the primordial non-Gaussianity in the CMB map, and the y-axis is the output value. So the training set value and test data value pretty well align with this y equals x line, which means the machine is able to recognize this input non-Gaussian pattern, and therefore reconstruct, will basically tell you what is the value of this non-Gaussianity FNL into this in this map. And the right plot is the least square fitting of the predicted value A and the true value, and it shows the constrained value of the slope A and B intersections is an order of unity. It means the machine can reconstruct this value at the same level of the Planck's 3-point correlation function. So this paper, we are basically writing it up. And the second thing is about recovering the underlying cosmological parameters. And this is the way we want to see whether the future machine can replace the traditional 2-point correlation function, the statistics. And this is the power spectrum of the CMB, and we can use this data from the previous CMB map I showed to constrain cosmology. So the underlying curve, you see there's a curve going through all the data, is the lambda CDM predictions, in which Einstein's cosmological constant take about 70% of the universe energy budget, and plus a cold dark matter component, where the cold dark matter is about 26%, where our visible matter, which includes you, me, and also the table, the elephant, etc., all of this, is only 4%. So that is the standard cosmology lambda CDM, so Einstein's cosmological constant, or you can call it dark energy, plus dark matter, plus visible matter, which is atoms. Fit the data really well. Can you believe this? This is just going through all the wiggles, etc. And plus the inflationary scale invariant power spectrum, etc. So now, I want to show you this power spectrum is sensitive to many of the important physics, such as the Russell anisotropy, the inflation, the dark energy, the background crust oscillation. In fact, this peak, the second and third peak ratio would tell you the ratio between the visible matter and cold dark matter. The number which I just mentioned, 4% of visible matter and 26% of whole dark matter, is derived from the ratio of this. And realization and also the small scale anisotropy. So this is the result from the typical two-point correlation function, the Planck power spectrum, which I involved when I was a postdoc. You can see these are the constraint value of the fundamental parameter of the universe. So Ns is the tilde of the scalar perturbation, H0 is the Hubble constant, invented by Edmund Hubble in 1920s. So this indicating how fast the universe expands. The unit of that is kilometer per second per megaparsec. And the fraction of dominant density is about 70%, and fraction of matter density is about 31%, and so on. Finally, it's the age of universe. What a fundamental parameter that is. Age of universe is 13.8 billion years. That is the longest time of physical reality. Think about how fundamental. There's nothing longer than the universe. So I'm pretty sure that in ancient time, the Aristotle, Plato, all of these philosophers think about that question. What is the longest time of physical reality? Of course, by then there were only possible physical debate, like philosophical debate. But now we can answer these philosophical questions into quantitative science by using quantum science. Even give you an error of that. So by using machine, we can also do this. That's why I'm fascinated by using CFPC. So this is the input value of the Hubble constant by training order of 1,000 maps of the CMB, and this is the output. You can see they are pretty well aligned for different input value of H0. And also this is the baryon densities, and this is about input of the amplitude of the scalar perturbations, and this is about the tilt of the scalar perturbation. They can also recover this very well. Right? So this is another paper I'm writing up. So basically, that's one of the powerful applications of the machine. Okay, so what I told you is about the early universe. And as the universe evolved to about 1 billion years, the gravitational potential gradually attract more and more matters, including atoms and also dark matters. And they start to form the first stars and galaxies. So at about 1 billion years after the Big Bang, the gravitational potential attracts a lot of matters. Therefore, the first star and galaxy will emit a lot of ultraviolet radiations. And these UV radiations start to reionize neutral hydrogens and make the universe ionize again. So in this video, you see that gradually the seeds of ionization, the first star and galaxies, gradually grows bigger and bigger of the ionization bubbles, and eventually eat out all the remaining neutral intergalactic mediums. So it's a fascinating video to look at, and I compress this billions of years evolution into 20 seconds. Now you see the universe is almost ionized. So this is indeed the tool. This is indeed the aim we want to probe. And the unique tool in South Africa is this hydrogen epoch reionization array, or HERA. This is a low-frequency radio telescope, also in the Northern Cape, in Karoo Desert, 2 kilometers away from Meerkat SKA, that measures the spatial fluctuation of the 21 emission around 1 billion years after the Big Bang. So the lower right corner is myself standing in front of it. In front of this 14-meter dish of HERA. And you can see this is the US and South Africa collaboration project. In these 4 years, I'm leading South Africa for this project and coordinating a few projects. Okay, so the unique aspect of machine learning is to recognize non-Gaussian features in the data. So this is the time evolution. As you can see, at early time, the universe was filled with neutral hydrogen. So there's a pretty positive value of the brightness temperature. And then as the first star and galaxy form, they will gradually reionize the universe, ionize this neutral hydrogen. Therefore, more and more neutral hydrogen will be ionized. So therefore, eventually it will be a zero brightness temperature. So if you plot the peak probability distribution as a function of the brightness temperature, at higher redshift, it's just one of these bonds, which is non-Gaussian, but just one bond. And then as the universe evolves, the redshift going down, then this bond will become lower and lower, but zero value will become higher and higher because the universe becomes gradually ionized. So then we can see if we don't use machine learning, we just use a 21 centimeter power spectrum analysis, just giving the data, do a two-point correlation function, that is power spectrum analysis, then we still can get some constraints on the physical parameter of the reionization. So So this is the virial temperature of the minimal virial temperature for the first ionization galaxies, and you can see is the ionization efficiency of the first galaxies. So you can see just by using power spectrum, we do receive some constraints on these two parameters by simulation. However, if we use machine learning by doing CHPC, you can see the result from which is the red constraint is much tighter, much better constraints of the parameter than the power spectrum. And why is that? It's because machine from CHPC can recognize those non-Gaussian patterns, can recognize the distribution of the brightness temperature in the volume, and being trained, it can extract additional information, maybe 3-point correlation function, 4-point correlation function, 5-point correlation function from the data, so that it will perform better than the 2-point correlation function. So you see the machine here, which is the red dashed line here, it does provide more information that the constraint is actually tighter than the power spectrum. So to prove this, we also did another exercise. We just intended to make the volume, make the whole realization volume to be Gaussian. Then if the machine, then there's no additional information, right? Then the machine should perform the same as the power spectrum analysis. And then yes, that's the result. So if we just intended to simulate a Gaussian universe, which is not a real universe, we just intended to simulate a hypothetical universe where 2-point correlation function is sufficient to describe all of the statistical properties, then we'll get the same result. Then the green dotted line is what machine learning will give you. Then we'll have almost a similar error of the parameters than the power spectrum. So this really proves that the machine can really recognize those non-Gaussian features and extract it out and help you to understand the physical evolution of the EOR. So my conclusion is the advantage of using machine learning to study cosmology is to extract non-Gaussian information from data. And these non-Gaussian features include the primordial non-Gaussianity from the CMB, which arise from the exotic inflations, some exotic isocurvature perturbation at the early universe, and also the patchy reionization process, which arises because of the ionization of the first stars and galaxies. And by the way, physically, those first stars is definitely not like our sun, because it was very metal poor. There was very little metal inside the star. It's mostly hydrogen and helium. And CAPC in general can be used to deal with the astronomical data with Meerkat, SKA, and help both in data analysis and numerical simulations. Lastly, I just want to highlight that there is a lot of radio astronomy surveys in South Africa, such as the Meerkat and SKA, the hydrogen epoch of realization array, and also the HIRAS telescope. So there's a lot to explore with CHPC. That's all. Thank you.
Okay, we are slightly ahead, so you've got 2 minutes possibly for questions. And this is a gift. Thank you very much. Are there any questions for our speaker? Yep.
Yes. Could you mathematically bound the Earth from your model to observation? So can you guarantee, or give bounds for your uncertainty?
Yeah. So unfortunately, no, because Earth is too small. So Earth is an emergent phenomenon in the universe. So let's say. Nico is wearing a blue jacket today. Does that information help me? That is a phenomenon in the universe, right? Can I use that information to constrain cosmology? Can I use that information to probe anything at the early universe? No, because he is too small. In fact, we are too small. This Earth is too small. Our own galaxy is too small. So we are too small, and that we are just, our own galaxy is just a single particle in the universe. So its entire thing is an emergent phenomenon. So therefore, we cannot predict the existence of Earth.
Thank you very much. Sorry, just a second. What happened here? Sorry, something. I have this recording message. Okay, sorry, the second attempt. So good afternoon. Thank you very much to the organizers for the opportunity to present NITEX at the CHPC National Conference. My name is Francesco Petruccione, and I'm the interim director of NITEX. Yeah? So what I would like to share with you is some basic facts about NITEX, and encourage you all to become NITEX associates so that you can help us make NITEX a success. NITEX is a new national research facility, yeah, and it might be the first new national research facility according to the new policy document of DSI around national facilities. Yeah. So NITEX is an institute that emerges from the previous National Institute for Theoretical Physics, which was administered by NRF as a center of excellence. And as you know, centers of excellence, after 3 times 5 years, a sunset clause kicks in, and they need to find some other solution to be sustainable. Yeah. In the case of NITEX, the solution that was agreed upon with DSI and NRF after extensive consultations and several committees that wrote various documents, like a document that confirmed the scientific need for such an institution, a roadmap for the transition, and so on and so forth. And it was agreed that this national institute should rest upon 4 pillars. Yeah? Research being, of course, one of them, but also training, engaging, and opening up to the African continent. Yeah, and all these 4 pillars should have the same strength. Yeah. Sorry, I'm just quickly checking that I. Okay, I will check this now. The Benjamin will let me know if I'm running over time. Yeah. So what is really important to know about NITEX is that it is an institute essentially in charge of supporting research, training, and engagement activities in the basic sciences. Yeah. So it is not anymore exclusively theoretical physics like NITEP, but also astronomy and astrophysics, mathematics, statistics, data science, and then the quantitative and computational aspects of finance, of bioinformatics and quantitative biology, and last but not least, Earth systems and climate change modeling. Yeah, so you see, it's a big, ambitious institute that covers a various array of disciplines. Yeah, but as the figure that you see indicates, yeah, it is crucial for NITEX to find a point of convergence, yeah, where these 8 disciplines meet each other and start working together to be more than the sum of the parts. Yeah? I like sometimes to call NITEX not a multidisciplinary, not a transdisciplinary, not an interdisciplinary institute, but an undisciplinary institute. Yeah? Because we want to put the big challenges that South Africa, and the world face at the core of the activity of NITEX, yeah? and focus around a limited number of research questions that none of the discipline could solve on their own. Yeah, so that is the basic philosophy of what we want to achieve, and that will also be the glue that keeps it all together. Yeah. So NITEX, for those of you that are not familiar with it, has several activities along the various pillars. Yeah, we have internship and PhD and bursary programs for our students. We organize regularly schools. We have a program of mini schools. We have that are monthly events dedicated to a specific topic. Yeah, we have math schools dedicated essentially at high school learners, but also at their teachers. Yeah, we have a South African theory and computational school that offers honors level courses that are just broadcast across the country and essentially across the world. Yeah. and we try to find a solution so that students at their own university can also get credits for attending these courses. Yeah, we have a partnership with the Carpentries, which is an NGO that provides basic training in programming and other computational literacy topics. Yeah, and they're very popular not only to students but also to some maybe junior members of staff at various sorry, at various universities. Yeah, since recently NITEX is also part of a cluster of research excellence around artificial intelligence, which is a collaboration which is between a group of European universities called the Guild and ARUA, which is a grouping of Africa research universities, so that helps us opening up to Africa and Europe and many other things. We are also involved in a magazine called Visarco, that is also a magazine with the aim of popularizing, let's say, mathematical sciences and surrounding to a more generic public. Yeah? Just to let you know, the size of NITEX. Now we have around 250 associates. Yeah. And here you see the distribution per university, but maybe it's nicer to see it clustered per provinces. So you see at the moment, but things change continuously. The largest number of associates is in the Western Cape, followed by Gauteng, KwaZulu-Natal, Northwest Province, and then a handful of associates scattered in the other provinces. And the zero that you see here is, in the meantime, since this picture was made, no longer at zero. We have associates in that province as well. Yeah. So what is also interesting is how the associates are distributed now. Yeah, as I mentioned, NITEX was originally NITEP, the National Institute for Theoretical Physics, but in the meantime, theoretical physics is no longer the majority. Yeah? So in a democratically run NITEX, theoretical physics doesn't automatically have the majority. Yeah? Other disciplines are catching up quickly. One has, of course, to keep in mind that not all disciplines have the same number of potential associates in the country. Yeah? Some are more popular than others, if popular is the right word. Yeah, but you can see that there is a big uptake already in astronomy, astrophysics, in the biosciences, mathematics is doing very well. Data science is also doing very well, and we are increasing and working on increasing the number of statisticians, of quantitative finance people, and climate and earth systems modelers in NITEX as well, so that maybe in a year or two, this pie chart will look a little bit more uniform. Yeah. The reason why it was really nice to be invited to speak about NITEX today is that eventually, after a long procedure that took almost 2 years, DSI and NRF assigned the NITEX consortium. Yeah, so we have now an official NITEX consortium, so that slowly all the interim structures are being dismantled and permanent structures are being put in place. Yeah. So, and as you see now, NITEX is now a consortium of nearly all universities in the country and aims. There are just 2 universities missing, and we will make an effort in future to get them involved as well. Yeah, the headquarters of NITEX will be based I can say now in Stellenbosch. And these 26 institutions, sorry, here you see the 2 universities that are not yet part of the NITEX consortium, but we will reach out to them and make sure that they will be part of it as well, so that this will put then NITEX on a very unique setting, because we're probably first national institute that has all universities in the countries involved. Yeah. to run such a big operation, we need a structure. Yeah. And at the moment, we are structured into 5 nodes. Those were the parameters that DSI and RF issued in the call for NITEX. Of course, ideally, in a second stage, we would like to have a node in every province, but for now we have only 5. Yeah. And inspired by the distribution of associates that I showed previously, we have 3 provincial nodes, yeah, in the Western Cape, in Gauteng, and in KwaZulu-Natal, yeah, which collect all the universities in those provinces, and 2 regional nodes, yeah, that one across the Eastern Cape and the Free State, yeah, and one that connects the let's call it the northern provinces of the country, yeah. And as I mentioned, ideally, because the last 2 regional nodes are geographically a little bit stretched, it would be nice to start working towards having a node in every province. Yeah? Each node has a kind of head of node, if you want to call it like that. Yeah. In Gauteng, it will be Wits. In KwaZulu-Natal, it's UKZN. At NMU, in Eastern Cape and Free State, it will be an NMU. And in the north, at Northwest University. Yeah. In the Western Cape, we have Stellenbosch as the main hub of the whole consortium, and UCT will assist in running the provincial activities. So this is how the consortium will be structured. Yeah. Just to tell you where we are, yeah, we started, as I told you, the conversion from NITEP to NITEC started in April 2020, when I was appointed as interim director of NITEX. And if you remember, that was the first week of the first hard lockdown of COVID. Yeah. So in February 2021, we started the proper implementation plan. And a few months ago, Stellenbosch University was awarded the NITEX consortium, and the plan is by 1st of April 2024, and this is not an April's Fool joke. The new NITEX will be launched, and all the legal aspects that are being put in place at the moment will be completed. Yeah. So. I'm asked very often, where will NITEX be hosted? Because NITEP, the predecessor institute, was hosted at STIAS, the Stellenbosch Institute for Advanced Studies, but we want NITEP to be hosted on campus. Yeah, we want it to be closer to academic staff and students. And this, what you see here, this garage door, yeah, is a wing of the current physics department. Yeah, and this wing that is a little bit L-shaped, but the L you don't see. Yeah. Will host NITEX. Yeah, the renovations have already started. You see the new entrance, dedicated entrance for NITEX. That you see it how it looks at the moment, and the renovations for the inside will commence probably in the beginning of the new year, because, as you know, December is not a good time to start building works in South Africa. So you see, we'll have offices and a seminar room and various other facilities, and they will look really very nice. And we will invite you all to come and visit us. Yeah, we have already a plan in place for the next growth phases of NITEX, to move then in a second phase in bigger premises that are just across the road. So in conclusion, just a few, because I think I still have a few minutes. Yeah. Just a few maybe more philosophical considerations. Yeah? You know, NITEX, as you see, is really will be a big research facility. Yeah? Because we have already 250 associates, and we haven't even officially started. Yeah, so it will have probably many more. Yeah, and the only way to make it work, because the associates are all scattered across all the universities in the country, is that we embrace from the beginning open science and open data principles, yeah, so that everything we do will be open. Every code we produce will be on GitHub, and every data we collect will be open data. Yeah, so this is one of the fundamental principles that we want to embrace from the beginning. Yeah. Connected with this is, of course, that we need easy communication channels, yeah, because all the associates are scattered across 26 universities. Yeah, so that's why we have already reached an agreement. I'm not sure with Google to use Google Workspaces as our main tool to communicate. Yeah. And having the communication in place, the collaboration will be essential. Yeah, one of the strengths of NITEX, because we have access to all the basic sciences and disciplines nearby. Yeah, we are very good at networking. Yeah, so we can really find collaboration partners for associates that are looking for some. Yeah, so that will be collaborating will be one of the strengths of NITEX. Yeah. And of course, as I mentioned at the beginning, we need some glue to keep it all together. Yeah, and the glue is just impactful science. We want to address real scientific challenges and solve them. Yeah, and the challenges should be across disciplines. Yeah, so we want people really to work together to solve problems that they wouldn't be able to solve on their own. Yeah. Of course, the transformation is one of the other challenges that we need to solve. Yeah. And the fact that we have already all universities in the country on board is already a very strong first step to indicate that we are on the right track. Yeah. A big institute costs a lot of money, yeah, to maintain. So we will have to do also efforts to look for sustainability. Yeah, maybe 100% sustainability for an institute in the basic sciences maybe is not achievable, but because we want to address serious challenges, yeah, we will have the opportunity to collectively apply for serious funding from international funding organizations and so on and so forth, and contribute at making the research and the training and engagement possible. Yeah. So this is in a nutshell the new NITEX, yeah, this new National Research Facility. And thank you for listening. Please visit, unfortunately, visit the NITEX website, which is www.nitex.ac.za. Sorry, I should have put it here, I forgot. And you can register for our mailing list, and you can apply to become an associate. Essentially, we just need your CV. Yeah. So thank you very much for listening. And if we still have a few minutes, I will be very happy to take questions. Thank you very much.
So I'm going to take back from the previous talk. So how to build a knowledge democracy. So what Lydia talked about with Ndau X and deep learning in Java, I want to mention like how we can create our own Ndau X, our own communities. How can we go from grassroots to greatness? And I'm going to talk about what grassroots means. But I want to share with you how you can create your own community with low and scarce resources. And want to start off with a question, like what is the best use of HPC resources, which Lydia also mentioned before. But I want you guys to you all to think about this more proactively, like what resources can help. Like machine learning is a really big application of big part of HPC, but what else can be done? And I want to introduce you to the stakeholders of the African AI community, which is you. So all of this community would be nothing without you, right? If you were not interactively participating. And I want to showcase what a community means. Like, it is so important to help share knowledge and bring capacity in African machine learning community. And the whole point of grassroots communities is to strengthen and enable a platform to start and collaborate on urgent pressing problems in Africa. And that can only happen when we come together as a community. And so how do we start? How do we build a community? So some things have been done. So WHO came up with this plan of One Health organization, like a One Health plan. But it doesn't always work. It does help in shaping economic matters, but to get social progress and to solve the African problems, you have to go a little deeper. So thank goodness we have grassroots greatness. And I'm going to talk about a paper which was published at ICLR, which is a big machine learning conference. And we talked about the grassroots participatory communities there. And we focus on this proverb that if you want to go fast, you go alone. But if you want to go far, you go together. So how do we build these communities of grassroots participatory that can enable communities in low resources to come up in society and solve urgent problems? So this was the paper, which is by Africans for Africans, and this has authors from various conferences coming together to build up this framework that you can use to create your own community. And I want to talk about these three main communities which talk about how to make communities for different events. So Masakane is an isiZulu word for build together, and it focuses more on NLP, and it focuses more on low resource African languages. It organizes Ndau roadshows. It does socials and major events, and the main focus of them is the fact that 2,000 of world's languages are African, but African languages are barely represented in AI. So if you could see the chat GPTs, or there's not much representation of those languages. Then Roya is an Arabic word for vision, to focus, they're focusing on computer vision. So they organize workshops for CD for Africa, they do socials, they make data sets and tools, so that it's not more focused on the developed countries' needs or all the big companies' needs, but more African needs, our needs. Right. And then Siswamke Biotech is also again isiZulu word. So yeah, and that means together biotech. So they focus on healthcare and biotech, and to bridge the gap between healthcare and biotech, and to bring people together, to work together. And one of the stats from Siswamke Biotech is they have done 4 academic workshops at major conferences, and they have raised 60,000 plus to fund students to go to the conferences. Then they have done 4 publications, which are really good, participating, collaborating with the members. There's over 400 members across the African continent. So they are really making a difference. And this is how, these are the main types of GPCs. So The one which was mentioned by Lydia is the event type. The deep learning Ndau, the Ndau X, the AI Expo. What I just mentioned is the topic ones, which is Maskhane, Roya, Sisonki Biotech, which is like NLP, computer vision, and biotech, and all that. And then there's affinity type, which is more underrepresented community for underrepresented people. So black in AI, queer in AI, and so on. And this is some of the research that is coming out. It is really making an impact. This is one paper on NLP from Masakane. This is another similar to like a language model, but for African languages. This is from Sisonki Biotech. They're doing biomedical relation classification. This is from Roya. They're doing computer vision research. And this is all people like you. And this impact is not just in Africa, it's also in the European continent, in Asia. So there's Kipu, Latin America, there's EEML, Eastern European Machine Learning, there's Southeast Asia. All of these big conferences are following our suit, following this grassroots community framework. And we follow a community first approach. So you come first and rest follows. We build the values around you to build trust, to build inclusion, so that you are comfortable with the skills that you have. So it allows anyone with any skills to collaborate and learn and build together. And you also make a ton of friends, you do networking, but this is only a glimpse. Right? And how are the roles and contributions? So first, you have the building members, the core members, those who lay the foundation, right? Who create the values, the vision. The contributing members who are more, who give more time. They give a commitment. They are the most valued members. Participating, who come for sporadic times but still are contributing. And exploring, who are just seeing what's happening. How do I contribute? How do I enter? Is this for me or not? And this is the roadmap. You have 3 phases. So in the phase 1, you gather a core participants, right? Then you establish an identity, a brand, something like Masakane, which was talked about earlier. And then you set up websites and initial collaborations so that there's no friction for members to join in. Then there's phase 2 of growth. You keep some regular smaller activities and less regular large activities so that you can grow the GPCs together. You can make it bigger, right? And phase 3 is more organizational structure. So this framework is for any small group of individuals with scarce resources so that they can build an online community within the span of 2 years. That's really important, and this has been done. And I want to highlight some business greatness from this, with some businesses that have been inspired by the Ndau or the Ndau X or related communities. So recently, Times 100 AI influential people featured some of Ndau people as well. And there's a lot of African AI communities that are focusing on African problems. So I want to ask again, what is the best use of HPC resources? Could it be to provide free compute to students or members? Or could it be like travel grants to conferences, or expertise, or connections, or building amazing products? What can we do together? And this is how I imagine the future of AI in Africa, to be built for Africans, by Africans, and we'll have communities for specific needs, for specific problems. And there should be collaboration between the communities and between the industries, which will help enable solve major problems. So I just want you guys to get involved, and Ndau X will be also held next year, and you can become anything you would like to. Like you can apply for a participant, poster presenter, volunteer, organizer, speaker, whichever things you would like. But the main point of this is how can you make your own Indaba X. So I hope you understood or got some insights into that. All right, thanks a lot. Okay, any questions?
Before you get a question, you get a gift.
Thank
you
you.
for coming.
Thanks a lot.
This is for you.
Yay!
There you go. Okay, are there any questions for Nilesh, please?
Yeah. I see a lot of sleepy faces.
You were too clear. You covered everything. There's no questions. And you've also, of course, oh, there is a question.
Oh, thanks a lot. I really appreciate that, yes?
I think for me, it's more to thank you for availing yourself for what you just presented here.
Okay, thanks a lot. I will give you context of Masakane. They also do NLP. Yes?
A very, very quick question.
Yeah.
Do you know when the Ndau X will be next year?
So mostly it's coming back to Wits in Joburg, but I still have to confirm. Yeah.
Thank you.
Yeah. But I will forward the message to the group and you will know. Okay.
Back to the back.
Okay, yes.
Sorry, if you could kindly just let us know in which countries Indaba X currently exists, that would be great.
Yeah.
Because given that, we have Francophone Africa, we have the Anglophone and Islamic Africa, just to understand where.
So currently Indaba X is run volunteer-wise in 36 countries. So like how Indaba X South Africa, you have Indaba X Nigeria, Indaba X Ghana, all of that. So it's there in every country. So does that answer?
On the website, will we be able to see what those countries are?
Yeah, you can see it on the main Indaba website, the Deep Learning Indaba, because IndabaX.co.za is mainly like South Africa, but there's individual websites for each country, like, so, but I can share it, we can take it on.